In this episode, a sporting stadium of record-breaking proportions.
Every day I walk around and am just marveled by the feat that this building actually is.
Taking engineering to new heights.
It's the longest continuous single arch span in the world, and really an incredible engineering feat.
And the pioneering historic innovations.
It's a real marvel of engineering, and it's a real privilege to be able to do this.
We're headed up there, 6,288 feet.
That made the impossible possible. In 2009, one of the most successful teams in NFL history needed a new home, having outgrown their old stadium. Relocating to Arlington, Texas, the Dallas Cowboys demanded an extraordinary structure.
The idea from the very beginning was really to create the finest stadium of its kind anywhere on the planet.
With such high aspirations, architect Brian Truby faced the toughest task of his career.
The engineering in the project was, for us, a particularly unique challenge.
But would ultimately create a structural masterpiece. The epic AT&T Stadium.
For us, when a patron enters this building, we want them to leave saying, gosh, I never have experienced anything like that.
Capable of housing 105,000 fans in a jaw-dropping 3 million cubic meters, the stadium measures almost 400 meters in length. Each end features the world's largest sliding glass doors, whilst the structure's spine is formed by the two longest unsupported arches in a building on the planet, holding up a state-of-the-art roof that can be opened and closed at will. This $1.2 billion stadium was conceived to be much more than a supersized football venue.
We knew from the beginning that the Dallas Cowboys would only be here 10 days a year. So we needed to make sure that this building would be alive and living for the remainder of the year.
With the Texan climate ranging from winter snowstorms to scorching summer days, designers had to control the building's environment. Their starting point, a gigantic roof.
The roof structure itself is equivalent to the weight of 99 Boeing 777s.
And they'd need to support it without interrupting the view.
One of the incredible challenges with this venue is creating that large column-free space.
The huge forces that come into play to keep 104 million cubic feet column-free are enormous.
So how do you hold up the largest single-span roof in the world without any supports? It's an engineering feat that would be impossible without the great innovators of the past. Since the dawn of time, engineers have struggled to hold things up. The Temple of Artemis may have been one of the 7 wonders of the ancient world, but its vast roof needed over 100 columns.
What?
To stop it caving in.
Phew.
The Romans decided to go lightweight, the Colosseum's huge ring of awnings protecting spectators. But sadly, not those center stage.
We're on strike.
The solution for the stadium in Arlington would actually come courtesy of a construction conundrum faced during the 19th century in the Portuguese city of Porto.
In 1875, engineers were building a new rail line between Lisbon and Porto. But when they arrived here on the banks of the Douro River, their progress ground to a halt. At the time, a span of this size was considered extremely challenging, and so a bold and innovative new approach to bridge design was required.
With his specialist skills in metal structural work, French engineer Gustave Eiffel was commissioned to tackle the 160-meter void.
Now, the challenges that Eiffel faced in building his span were just immense. In addition to the width of the span, the river is also very fast flowing. It's up to 20 meters deep in flood season, and this meant that it was impossible to put piers in the water.
With no obvious way to support the bridge, Eiffel proposed an audacious solution: an enormous single arch built into the sides of the riverbank.
An arch on this scale seemed an impossible task, but Eiffel proved everyone wrong. And this is the result of his achievement. Isn't it an exquisite example of engineering? In order to make this a reality, however, Eiffel had to completely rethink arch design. Now, for bridges, the arch is actually a really brilliant shape, but it does have its limits. And I can illustrate that using this piece of card. If I place this card between two stones that represent the bridge abutments, and I place a load on it, it supports that load using compression, and the compression flows down through the arch and into the abutments. But of course, in a location like we have here, where we need a much larger span, we have to increase the length of our span, and our arch becomes much more shallow, and then the forces of tension start to take over. And as my structure is loaded, you can see that it struggles to support that load. And this was precisely the problem that Eiffel faced here at the Douro.
Solid reinforcement would simply make the arch too heavy. But Eiffel came up with an inspired alternative.
Definitely reconsidering my shoe choice for today. Bad choice of shoes today.
Luke is heading into the heart of the solution.
So here I am dangling halfway up of Eiffel's magnificent arch structure, and I have to say it's a real privilege to be able to do this.
The secret of Eiffel's success was to harness the strength of another simple shape within a network of open trusses.
And looking at the structure, you can see all the different elements of the truss, all the different parts holding the bridge up. And by making use of a simple system of triangles, Eiffel was able to create a structure that was both light and very strong and stable, and had a bigger span than ever before. And it's a real marvel of engineering. Simply genius. So to understand how this truss system works, we can make a simple comparison between two shapes that are commonly found in engineering. If we look first at the square, you can see that if I push down on it, it doesn't take long until that square deforms and collapses. And that's because the square lacks inherent stability and rigidity. But you can see if I take this triangle and I apply a vertical load to it, you can see that it's able to take that load. And that's because these two side elements go into compression, this bottom element goes into tension, and there's equilibrium created at the point where I'm applying the load.
By exploiting simple physics, Eiffel's trussed arch created engineering history by spanning the greatest distance of its age.
Eiffel's experiences here ultimately provided him with the engineering knowledge and techniques to go on to create his most famous structure, the Eiffel Tower. Not only that, but in creating this, he helped to completely redefine arch construction. And today, arches form critical parts of some of the most impressive and iconic structures all around the world.
In Texas, engineers would take Eiffel's innovation to record-breaking proportions for a building.
It's the longest continuous single arch span in the world. So we're really taking kind of inspiration from some of the bridge structures that are out there and applying to a building.
So what you're looking at are two primary arches that span about 1,400 feet each. The size of the trusses themselves, they're about 14 feet wide, about 35 feet tall.
The stadium's twin backbones soar to almost 100 meters above the playing field. Each archbox truss weighs over 3,000 tons, creating 8.6 million kilos of thrust into each of the 4 colossal concrete abutments.
The concrete abutment, then, what you see above ground, takes all those forces directly into a large concrete footing below ground. It's about 4 times larger than what you see above ground.
Each abutment required 10,000 cubic meters of concrete. Once completed in July 2007, work could begin on erecting the awe-inspiring arches.
They basically would start at the abutments on each end, and they would start with a single truss, and they would build towards the center.
Over an 8-month period, a series of 6 shoring towers were erected to support each span, before the connecting keystone piece finally fell into place. Only then can the arches take the strain and eliminate the need for even a single column to spoil the view.
Placing that keystone piece in the truss, that's really the first time after that that the structure's allowed to load on itself.
But they still faced further challenges and would have to turn to the great innovators of the past.
The difference in height between the front of this carriage and the back of this carriage is about 13 feet.
To produce more impossible engineering. In Arlington, Texas, engineers have created one of the largest sports and entertainment venues on Earth.
What you see here really is the most transparent stadium in the world. And you can see the arches, for instance, that span the entire length of the building, about a quarter mile.
For architect Brian Truby, this stadium has changed the face of arena design.
From an engineering standpoint, there's really very few structures like this.
During 2008, after 8 months of construction, the steel arches were finally in place, allowing engineers to continue with the stadium's roof.
So the roof itself actually covers about 660,000 square feet. And the reason for the shape of the roof tracks back to Texas Stadium.
As the former home of the Dallas Cowboys, Texas Stadium was renowned for its distinctive domed roof structure. Keen to keep tradition alive, the owners were also determined to retain another historic detail.
The iconic hole in the roof is very signature to us. Someone once said it's a hole in the roof so God can watch his favorite team.
But to cope with all weathers, a retractable roof sitting on top of the arched dome was the only viable option, creating a seemingly impossible problem for project engineer Guy Decker.
One of the largest challenges that we had is that arch shape of the roof structure below. It's not natural for a retractable structure to be on top of that. It creates a very steep slope, particularly when you get to the ends. At the very steepest level, we're at a 23-degree angle, which is really the steepest retractable roof that's ever been done.
So how do you maneuver a 760-ton roof panel up such a steep incline? Achieving this might not have been possible without a high-altitude innovation from over 150 years ago. Architectural historian Jen Mason-Garb has come to the White Mountain National Forest in New Hampshire to see an inspired invention many believed couldn't be built.
With an elevation of 6,288 feet above sea level, more than 1,900 meters, Mount Washington has long been the site of exploration since the late 18th century. But it's got bad weather and rough terrain and an incredibly steep grade, and so only the most adventurous climbers were able to make it to the summit to see the stunning views.
For this scenic beauty to be enjoyed by all, a solution would ultimately come from an unlikely source. During the mid-19th century, Sylvester Marsh was a successful businessman in the meatpacking industry. But it was his passion for climbing that would lead to his biggest accolade. Having been trapped on Mount Washington in a flash storm, he set about designing his dream, a railway capable of transporting tourists to the top of the mountain.
The basic problem Marsh faced, of course, is that this grade is simply too steep for a regular railway. In a typical car, the wheels would have spun without any friction, and the train would have slid right back down the mountain.
To overcome the extreme gradient, Marsh broke the mold, creating a steam-driven train that would literally grip the track.
When it opened in 1869, the Mount Washington Cog Railway was an engineering marvel of its day. It travels a total of about 3 miles, 2,700 feet at the base, and we're headed up there 6,288 feet above sea level, making it the second steepest mountain cog railway anywhere in the world.
And its secret lay in an incredibly effective system known as rack and pinion.
Here's a simple demonstration about how this rack and pinion system works. If we imagine for a moment that this plank of wood is the side of the mountain and I'm the train, I'm obviously going to try to get up the mountain, and you can see that I slide back down. However, if we apply a rack to the side of the mountain, and I'm still the train, my feet act as these pinions in the rack, and you can see that I can easily climb up the side.
On Marsh's system, the pinion is a toothed cogwheel, positioned centrally on the underside of the carriage to fully engage with a rack which lies between the track's running rails.
You can hear the pinion engaging into the rack, providing that extra connection and the friction that's needed to overcome the steep grade. And in fact, we're now on the steepest part of the track, called Jacob's Ladder. There's a whopping 37% grade here. And in fact, the difference in height between the front of this carriage and the back of this carriage is about 13 feet.
But Marsh's engineering genius didn't end there. To safeguard the train from rolling backwards, the cogwheel or pinion also engaged with a ratchet brake, meaning the cog could only move in one direction. If the train started to slide down the mountain, the ratchet would automatically drop, locking the wheel in place. This remarkably effective backup system ensured Marsh's train always reached its final destination.
Marsh's design was an engineering marvel. When it opened on July 3rd, 1869, tourists flocked to take the train and come up to the top of this mountain and enjoy this incredible vista. And in fact, Marsh's design became the blueprint for other cog mountain railways across Europe and around the world.
Engineers at the stadium in Texas have taken this inspired design from the railways to new heights. As its cutting-edge rack and pinion system guides the 760,000 kilogram retractable panels over the steeply inclined roof.
One of the challenges with a retractable roof on a domed surface is, of course, the curvature. So each of the panels, as they move then down the tracks, they travel about 100 feet vertically.
During construction in 2008, engineers would tackle this incline by mounting over 400 meters of mechanized railing onto the arch structures.
The amount of engineering that went into this was really massive. You have structural, electrical, mechanization.
The 6,000 square meter panels are then made mobile with the rack and pinion system.
You can see the rack here, and then the gear pin here will interlock with this, so it's an extremely robust connection that very directly connects the roof to the retractable portion.
The system is so precisely engineered, the gigantic roof needs relatively little muscle to move it.
The retractable roof is powered by a series of 7.5 horsepower motors. Each side is powered by 64, so it's roughly a Corvette engine pulling and pushing the roof as it moves along.
When closing the roof, the motors have to generate nearly 1,000 horsepower to overcome the demanding 23-degree incline. Whilst opening them creates an altogether different challenge.
There's a lot of energy generated as they move back down because of the weight of the panels themselves.
With the motors now acting as brakes, the roof reaches its final position after just 12 minutes. And when combined with the world's largest sliding glass doors, this awesome structure offers a unique experience.
When everything is open, you really have almost an outdoor experience that you would get in an outdoor venue. I think that flexibility and that uniqueness is what sets the stadium apart.
But to truly rank amongst the world's most revolutionary buildings, engineers would once again turn to the great innovators of the past.
Wow, this is incredible.
To create more impossible engineering. In Arlington, Texas, engineers have created a modern structural marvel.
This building is about 3 million square feet. The largest stadium built to date is about 2 million square feet, so we're a third larger.
Boasting a gigantic retractable roof and the world's largest glass sliding doors, the structure literally embraces the elements. But if it was to succeed as a year-round multi-event venue, the sweltering summers would demand more technology.
We really felt like our fans deserved a venue that would be able to be climate controlled, and mainly for the heat, because it gets really hot down here in Texas.
Keeping the spectators comfortable, whatever the weather, would pose a huge engineering problem.
There were two big influences, the external heat hitting the building and heating it up, and you've got 80,000 plus fans generating heat. You've got all the technology, including video and sports lights. All those things create a particular challenge.
So how do you keep such a vast stadium at the perfect temperature? To find the solution, its designers would have to look to another great innovator of the past. Man has strived to keep cool for centuries. Roman Emperor Varius Avitus demanded mountain snow be brought to his garden during the summer to make the most of the natural breezes. But unfortunately, his comfort was short-lived. In 2nd century China, it's said that inventor Ding Huan created a mechanical fan system to provide the perfect temperature for a room full of people. Except, that is, for the unfortunate operator. But it would be the early 20th century before a predicament in the print industry inspired one of the coolest inventions in history.
In 1901, a young engineer called Willis Carrier was summoned to a publishing company with a problem. Because the factory printed in colour, the paper had to go through the presses multiple times to build up those different layers of ink. But because of the heat and the humidity, the paper would swell and shrink every time it was put through, and that would mean the colours ended up not being aligned, ruining the prints.
25-year-old Willis Carrier's idea relied on a simple but very effective scientific solution. Physicist Andrew is heading into an artificial jungle to put the concept to the test.
We've come here to the tropical biome of the Eden Project in Cornwall. Now, it's not especially hot in here, it's about 25 degrees, but it's very humid, above 90%. Here we have a modern reimagining of Carrier's invention. We've got a nice big fan here on the back, and on the front we've got this spiral of copper tubing. So what we're going to do is pump some cold water through that copper tube. We're going to suck the hot, humid air from all around us in through the back of the fan. And as if it wasn't enough of a challenge taking on the jungle, we've also got this kettle back here, which, when it starts to boil, is going to produce a lot of steam. Down here, we have our reservoir of nice cold water. It's full of ice packs. And inside here, we've got the pump. So what we're going to do is just start the pump up. And over here, just switch on the fan. And you can see this hot, steamy, humid air is being sucked through the fan.
As the water vapour in the humid air hits the cold pipes, it condenses, turning it into a liquid state.
And even though it's only been on a very short period of time, it's already sucked all this water, this humidity, out of the air.
And Willis Carrier's method to reduce humidity at the publishing company had another welcome side effect.
And on this side, it's actually quite pleasant. It's lovely, it's cool, and it's very dry.
The dry air was also at a lower temperature. The modern air conditioner was born. Factories and hospitals would be transformed by its technology, until in 1922, the advent of a centrifugal chiller allowed entire buildings and department stores to enjoy the comfort of his engineering innovation.
Today, air conditioning units are completely ubiquitous. They allow us to control ventilation, to clean air, to dehumidify, and most importantly, to control its temperature. Willis Carrier's invention truly has made the impossible possible.
Engineers at the mega stadium in Texas have taken Carrier's groundbreaking invention to a staggering scale.
What you'll see as you look across the top of the upper bowl are huge ducts. Many of these ducts are about 6 feet in diameter, so you can actually walk through the middle of them.
The system can throw out 11,000 tons of cooling capacity. But the key to keeping the spectators comfortable is directing the air's flow using the laws of physics.
What they're doing is delivering a curtain of air that washes down over the surface of the seating bowl. So we're really not air conditioning all 104 million cubic feet. We're actually air conditioning a zone about 10 to 12 feet tall.
This downward flow of air-conditioned air blanketing the spectators remains in place because of its density. As it's cold, the molecules are packed close together, increasing its weight, whilst the low-density hot air rises, accumulating in the vast space in the domed roof.
The size of the interior is one of our key physical properties that allows us to separate the cooled air from the heated air and keep the seating bowl cool.
Despite their cutting-edge climate control, to truly become a 365-day venue, engineers would face perhaps their most important challenge. to create a supersized surface to suit all needs.
We knew that it needed to be a venue that would not just house the Dallas Cowboys. We wanted to be able to be flexible so that we could move our field out to grass, or grass to concrete, or concrete to wood.
To create a super flexible surface, engineers would have to seek inspiration from a structural masterpiece from the past. Civil engineer Alfred Castillo Jr. has been given privileged access to an engineering icon that has been closed to the public since 2008.
Wow. This is incredible.
Opened in 1965, the Astrodome in Houston redefined sports architecture.
Prior to the Astrodome, stadiums here in Texas, they were built completely open to the elements. But coming to a baseball game in the middle of a Texan summer isn't exactly a great deal of fun.
Legend has it that developer Roy Hofheinz was moved to build the stadium after his young daughter complained of the heat and mosquitoes when they attended ball games together. The result was a $35 million+ stadium that could comfortably house the Houston Astros away from the glare of the Texan sun.
It was the world's largest indoor arena with a circumference of nearly half a mile. At 350,000 square feet, it made it the largest air-conditioned room on Earth.
But despite its record-breaking statistics, 60 meters above the grass playing field lurked a small but significant problem.
Players used to complain that the lucite in the dome roof would reflect light, and therefore making it virtually impossible for them to catch a fly ball. Some of the panels were painted white, but then that led to another problem. The stadium grass started turning brown and eventually died.
Having to resort to painting the mud green, the stadium needed a solution fast. Two American engineers, James Faria and Robert Wright, had the answer. The pair developed chemgrass, a new synthetic turf consisting of a carpet of nylon grass blades stretched across a thin rubber base. After its trial at a Rhode Island school, the innovative product would be rolled out at the magnificent Astrodome.
And in 1966, the Houston Astros played their first ball game on a fully artificial field that, in honor of the stadium, it was renamed to AstroTurf.
This piece of engineering genius would provide a resilient playing surface for nearly 40 years, whilst its portable nature also allowed the Astrodome to host anything from basketball to motor racing until its closure.
AstroTurf changed sports architecture around the world, and the Astrodome provided the blueprint for an indoor multi-purpose venue.
You could fit 3 Astrodomes into Arlington's mighty stadium, whilst its pioneering artificial turf has been taken to a whole new level.
You know, it's about 120,000 square feet of surface area, and it's really the stage. What you see here is the result of 30 or 40 years of technological advance and creates really the finest playing surface.
During construction in 2009, it would take 9,500 meters square of the state-of-the-art synthetic turf to cover the stadium's concrete substructure. As well as satisfying the Dallas Cowboys, It also proved to be the perfect engineering solution for a multi-event venue.
Synthetic turf really rolls up just like carpet, rolls back out, takes about 10 hours.
We have this surface for the Dallas Cowboys. We have a completely different field for college football. We've had grass in here for soccer, and we have had basketball here as well. I certainly think the multi-use aspect of it will be one of the legacies of the stadium.
But to create a venue that will truly make its mark in history, engineers would need to turn to yet another great innovation of the past.
It was here, at Wimbledon, that the BBC's first live broadcast of a sporting event would take place.
To produce more impossible engineering. Arlington's colossal billion-dollar stadium is the largest dome structure in the world.
It truly is a one-of-a-kind venue and really an incredible engineering feat.
This building has really changed the way these buildings are perceived.
Despite its record-breaking statistics, in the face of stiff competition, the stadium has had to push the boundaries even further to pull in the crowds.
For us, our biggest competition is not the team on the other side of the ball. It's network television.
You can set up one of the finest TV, surround sound, high-tech environments in your own house. So what we had to do here was be better than that.
So how do you create an unparalleled viewing experience for every fan in such a vast stadium? This huge challenge would have been impossible without one of the 20th century's greatest innovations. London's Alexandra Palace, an iconic building that was once at the centre of an engineering phenomenon.
At the beginning of the 1930s, the race was on amongst some of the world's finest minds to develop the first universal, standardised broadcast television system.
Scotsman John Logie Baird had invented a mechanical method of transmitting a moving image, whilst in the US, Philo Farnsworth had developed a rudimentary electronic version. But engineers were intent on improving their pioneering technology.
Leading the charge in the UK was a team of British scientists led by the Russian Isaac Schoenberg, hard at work here at Alexandra Palace.
Whilst the idea of broadcasting moving images into people's homes was in its early stages, engineers were building on simple technology of the very first cameras.
The basis for recording any image is capturing light. And what we've got here is a simple model of a camera. So we've got a big black box and we've got this hole in the front. Let's go around and have a look, see what we can see. Well, actually right now, not very much, because that hole is so big that all the light is bouncing off the objects in front of the camera. It's coming through that hole and it's not really ending up anywhere in particular on the screen. We've just got a wash of light. So what we need then is a lens. And as our lens, I'm going to be using this magnifying glass. So if now we pop that, there we go, on the front of the camera, I can actually bring the scene in front of the camera into focus.
The technique of recording a moving image onto film for cinema was developed in the late 1800s. But transmitting it to be viewed simultaneously in another location was a much greater challenge. An ingenious innovation created several years earlier by Russian engineer Vladimir Zworykin would, however, offer a starting point. By 1931, he patented a camera tube known as the iconoscope. Within the tube, a captured image was projected onto a mosaic of light-sensitive material, breaking it into thousands of picture elements known as pixels. A sweeping electron beam then charged the pixels before they were fed out of the camera.
Zworykin's invention allowed us to turn a picture into an electrical signal, but it was how that moving image was transmitted and then replicated on a screen at the other end that's the really incredible part.
Schoenberg's team refines Zworykin's technology, creating the Emitron, the BBC's first industry standard camera. And by 1937, it was possible to broadcast live into people's homes.
It was here, at Wimbledon, that the BBC's first live broadcast of a sporting event would take place, with the men's final being beamed into homes across London.
And the hefty young man from across the Atlantic defeated the good-looking Continental 6-3, 6-4, 6-2.
The key to transmitting television pictures lay in how the images were extracted from the camera.
So imagine this is a single still image of a tennis champion. It's a bit hard to believe in this case, I know. What happens is that inside the camera, that image is scanned into individual lines, broken down like this. And then these lines are taken out of the camera up to the transmitter, transmitted through radio waves, which are picked up by the aerial on top of your home. Then they're brought down into your television, where these lines are reassembled again into a full image. And obviously, this has to happen very quickly. Oh, there we go. Schoenberg's Emitron camera system used 405 lines, what was then considered high definition. I'm not sure I can manage that many.
Schoenberg's 405 lines of data created one frame. To create a moving image, TV sets had to reconstruct 25 individual frames every second, fast enough for the image to appear to be moving.
And this illusion of movement is much the same as you get with a flick book. It's by looking at a number of still images in very quick succession, you get the illusion of movement.
Transmitted through Alexandra Palace's television tower, broadcasts like the Wimbledon final would mark the arrival of one of history's greatest innovations.
It's hard to imagine the modern world without television. From transmitting breaking news around the world to covering major sporting events, TV is now central to the way we communicate and are entertained. And without it, the world would be a very different place.
In 2009, engineers at the Giant Stadium in Texas redefined the live broadcast. Installing the world's largest video board.
There's about 10.5 million LEDs. It's about 26,000 square feet of video surface. It's really unparalleled in major stadia.
It doesn't matter where your seat is, there is always an unbelievable view. You don't feel like you're in the upper deck. You feel like you are a part of the action, that you can see the passion and the inspiration on the participants' faces.
During its construction, this colossal entertainment system had to be built around a 10-story structure. Its huge scale posed an enormous challenge for engineer Guy Decker. Further complicated by its position over 50 meters above the pitch.
The structure is 72 feet tall and 160 feet wide. It's 1.3 million pounds. You know, that's a weight of 40 airplanes.
This feat of engineering is so massive, it has to be suspended from the building's backbone.
So here we are on basically level 10 of the video board. We're about 170 feet off of the ground. We have the main arch trusses, which are spanning the nearly quarter-mile span. And then we have these box trusses, which are there to provide support to the video board.
These monumental arches have once again provided a critical engineering solution to this extraordinary building.
When we were all out here and they hoisted that board up, everyone was looking at the roof wondering, did it sag? That's such a feat to marvel over and to appreciate just how complicated the engineering was.
3, 2, 1.
Since opening its doors in 2009, this remarkable feat of engineering has attracted over 10 million visitors.
The first thing people do when they walk in, they go, "Oh, wow." It's really fun to watch people's reactions.
For architect Brian Truby, it's been a life-changing experience.
Seeing the building perform is one of the most gratifying things in my career.
By learning from the great pioneers of the past, adapting, upscaling, and making innovations of their own, engineers have changed the face of stadium design.
This venue proves that if you have huge aspirational goals, you can actually attain something that's never been attained before.
And have made the seemingly impossible possible.
You know, every day I walk around and am just marveled by the feat that this building actually is.